In this video, I introduce a vision-based lateral control for autonomous vehicles. Autonomous driving system mainly includes four modules. First one is environment perception. Second is trajectory planning. Third one is control. And the final one is actuator mechanism. Right now, we introduce visual-based lateral control includes two modules. One is perception and another one is control. That means this perception module uses observation. It means we get the image from the onboard camera as an input to this convolutional neural network to extract the low dimensional track features. Once we got this low dimensional track features, and then we put together with the car internal state as the input to the reinforcement learning neural network to predict the policy. Yeah, this is like a system called VTROCS, just like an environment. It means agent takes the action, and then the environment generates the reward, and the agent moves from a current state to the next state. Here we use F1 as, for example, as the perception module, and F2 as the reinforcement learning module. And we use this as a vision-based lateral control system from the image input and predict the policy. First, we introduce the perception module. It's a multitask learning module. That means we have this observation as an input. We have this convolutional network, including 5 convolution layers and 4 connected layers. We have 3 outputs. One is track 1, task 1, task 2, task 3. 1 and 2 is regression. Regression is we are just to predict the location and the post. And the second one is just predict the angle. It means hidden angle between the hidden angle and the lane angle. Third one is just use the softmax to see the distribution, normalize the probability for turn right, turn left, and straight forward. To use the gradient descent method to train the convolutional neural network, we need to define loss functions here because these are 3 outputs. So we have defined 3 loss functions. The first one is for this regression, second one for this regression, and third one for this softmax. The purpose to train this perception module is, when we put together with the control system, make sure when we have image input, we can generate low dimensional track features for the control module. So we need the training data set in a superminer to train this perception module. So we have the observation and we have labels, corresponding labels for these 3 tasks. And then we find the optimal parameters. And then once we have a new input, we just run forward path to get the low dimensional track features. And here, this is just how can we define the dimensions and the location, pose, the angle, and the turn definition for this for a car in a lane. And then once we get the low dimensional track features, and now we can use the low dimensional track features together with the car internal state, here like a speed. We put together as the state, input state for the control module. Control module right now use the actor-critic model. That means one actor, just this like the policy module, to generate and improve the module. And then this critical module just evaluate this estimate the Q function for given the state and the policy. And then we use the iterative way. Finally, we got the optimal policy. First, let's take a look to use the gradient descent method to train the reinforcement learning model. We need to define an objective function. This is the expectation of the cumulative reward, future discounted reward. And then we use the deterministic policy gradient theory. So we calculate that we can write the gradient of the objective function in this formulation. Here is two parts. One is the policy gradient. We use this policy as the actor. And this one, if we update this value, then we can use this term as use this Q as a critic to evaluate the policy generated by the actor. Right now, because the output is just the steering command, so we only have one continuous action. So right now, that's why we use the deterministic policy method. So once we get this gradient of the objective function, then we can update the model parameters of the policy network. To use the actor-critic model, we need to evaluate this Q value. Then we can use a Bellman equation to get an update. Usually, you directly solve this update equation. We cannot get guaranteed stable. That's why most of the time we use the WQ network with experience replay to find the Q, to estimate the Q value and the policy. Here policy is again is a deterministic policy. And then to use the target, so we need to define another loss function. Here this is the target. Here is the current Q value at the state S and action A. Because rather now the target, because it's a deterministic policy, so we just at this state, the policy, we can select this state, this policy or this action. So once we need, also we need to calculate the gradient of this loss function, and then we can update the model parameters of the target the Q network. Here is the gradient of the loss function. Here this is the this is the gradient, and here this is the difference. As M is the number for the mini batch size. So we don't need to train the target network because we can copy the parameters from the Q network. We can either wait a certain time step, copy one time, or we can use the slow or soft update. That means every time we just update, we copy from the policy network or from the Q network to the target slowly, every time we just change a little bit. It's called slow or soft update. So once we got this Q value, then now we can update the policy parameters through the gradient of the objective function. Also here we use a greedy policy for this action selection. So we need to use the greedy. That means this is a small number. Here is the transition probability. Only in a small project we randomly pick up a policy. Here we introduce Gaussian normal distribution. Here is the variance. And for the real-world design, we design real-world encourage the vehicle run along a lane center and head in the lane direction. That's for example, here is if this theta is small, that means very close to the lane direction. We get the positive reward. Otherwise, we'll get the negative reward. Here is we got the comparison between the simulation and the ground truth. It's the distance deviation, this angle deviation. You can see they are pretty close to each other. For more details, please check with this reference. Thank you. Bye.